Hi, everyone. Welcome to Graphs, Your Path to Success. I'm Vita Shubin. I'm a senior software engineer at Google working on search for food.
Hi, I'm Chuck Omozurike, and I'm also a senior software engineer working on the fleet maintenance team.
Awesome. So, today we're going to talk a little bit about graphs, specifically how to handle graphs in interview settings. So, we'll talk about how to identify and solve graph problems, what kind of data structures you can use to represent your graphs, and we'll go through a lot of breadth first search and depth first search. I want to really quickly point out that this talk does not imply that solving a question using graphs is always the optimal solution. In fact, you might be able to solve something with graphs, and there might be a faster approach or a less memory using approach. But in an interview, it's oftentimes really accepted and more than reasonable to talk through your thought process. So we'll try to go through how we identify these graph questions and how we know that this is one of the possible approaches.
Awesome. All right. With that said, let's just dive right in with a quick reminder on what a graph is. So, a graph is a structure used to represent entities and their relationships. Each distinct entity gets one node, also called a vertex. Entities that are directly related are connected with a line. Given a node, its direct connections are also called its neighbors. So we can see here that if you go back real quick, you can see here that uh, the different nodes here are all distinct, so there are no repetitions, and the ones that are directly connected are have a line in between them. Cool. Let's go through an example now. So let's say there are 4 students. Suppose that A, B, and C are friends, but only D is friends with A. Now, if we assume that friendship is symmetrical, i.e. if X is friends with Y, then Y is friends with X, then we get this undirected graph here below. Now, there are a couple ways that we can represent these relationships. So we can definitely draw the graph, but we can also use something called an adjacency matrix or an adjacency list. So on the top left there, you see a matrix. You see that so if you take the first row, which is A, you can see that A has true filled in for the columns B, C, and D. Similarly, if you look at the column A, you'll see that it's also filled in for rows B, C, and D. You can assume that things that are not filled in are false. So this Boolean matrix here will be able to show you relationships. One really neat thing about adjacency matrices for undirected graphs, if you draw a diagonal from the top left to the bottom corner, you'll see that the matrix is symmetrical. At the very bottom, you'll see the same idea, but as an adjacency list. So even though we call it an adjacency list, typically we use a set for really fast access, but it's the same idea. You have this map where the key is the node and the value is the set of its neighbors. All right, so another example here. We've got 4 students again. This time, A is friends with C and D, but nobody likes A except B, which is sad. However, we now get this directed graph, right? So we have A who's friends with C and D, and then we have B who's now friends with A. So the connections there are going to denote that. And there's no symmetry, right? So we get only one direction from one node to another node. Similarly, we can do the same exercise where we can construct an adjacency matrix and a list out of this. Now, if you look at the top left of the matrix, you'll see that in row A, columns C and D are true. In column A, though, only B is true. And of course, if you do the symmetry exercise, the matrix is not symmetrical. We can look at the bottom left and see the adjacency list, where row A is going to have C and D as neighbors, B is going to have A as a neighbor, but C and D are going to have no neighbors. Okay, so it could be kind of confusing which to use, matrix versus a list. Here's sort of like a comparison of them both. The main difference between the two of them is the creation time. So the time it takes us to create a matrix is going to be n squared time. So if there are n entities, then to create a n by n matrix, you need n squared time. But to create a adjacency list, you're just going to need n plus e times. So you just need to list the entities themselves and then their neighbors. Both of these work just fine. However, we're going to really prefer the adjacency list. We feel like it's more intuitive. And it just sort of always, it kind of just fits nicely for most problems. You really want to think about an adjacency matrix or list if it's really important that you check the relationship between two particular entities, or to get all the neighbors for a particular entity.
Awesome. Thanks, Chuck. So now that we know how to represent a graph, what kind of questions can we actually solve with a graph? So some of the most common questions that we can solve are things like whether or not two entities have a direct relationship, the shortest distance between two nodes, or finding whether or not there even is a path between nodes. And I'm going to go into each of these in detail in a second. So let's start with looking at our A and B direct friends. How can we use a graph to answer a question like that? Well, an adjacency matrix or list can actually help us solve this pretty easily. Looking at A in the adjacency map, we can see its direct neighbors. So for this example, we see A's direct neighbors are C, D, and E. So B is not in that list, so we know A and B are not direct friends. Pretty easy lookup, pretty easy question to answer. We could have also looked up B in the map, and we would have seen that A is not in that neighbor list as well. We can also answer things like the shortest distance between A and B, and this is where an adjacency matrix might not be helpful to us, but we can use breadth first search. So let's go a little bit into BFS really quickly. Some intuition behind it. When you're thinking about breadth first search, picture the edges of your graph as equal length chains and the nodes as physical spheres that you can pick up and move around. So we're going to pick up the graph by holding the node that we want to start at, and that's going to make the levels more apparent. It's going to drop them down into kind of distinct sections that you can see here on the right. So BFS is essentially going to visit one level at a time. So in this example, we would visit A, then ECD in some random order, then B. So how do we actually apply this to the question? To find the shortest distance between A and B using breadth first search, we're going to start at our starting node A. Okay, so right now we're at distance 0. Then we're going to visit all of its direct neighbors. So this will be E, C, and D. And we know these are all neighbors at distance 1. Then we're going to visit all of their neighbors, and we're going to increase our distance. So now we know that we've hit neighbor B, we're at distance 2, and we can be positive that this is the shortest distance between A and B. Okay, so another question that we can use graphs to answer is finding whether or not there is even a path between A and B. So I just did that with breadth first search, but let's look at how we can do it with depth first search as well. A little intuition for depth first search. Imagine that the graph is a bunch of forks in the road, and each road takes you to more forks. So you want to explore every road, and you have to take each road as far as you can go, basically up to a dead end, before you turn around and make your path back to explore the other forks. So let's see this in action. Let's find if there is a path between A and B using depth first search. Again, we're going to start at A, and we're going to kind of randomly pick one fork to follow, and we're going towards E. Again, we're going to pick a random fork to follow because we're still going on our path as far as we can. That's going to take us to C. And again, we're going to take C all the way to A. Now, A, we already visited, so this is our dead end here. And what we do now is we start backtracking. We start going back up our road. So we go back to C and we check if it has any other forks. It doesn't. We checked all roads leading out of C, so we're calling C good to go. Then we're going to backtrack to E. Does E have any more forks that we haven't checked? No. So E is good to go. Backtrack to A, but A does have another fork, so we're not done with this one yet. We're actually going to follow A all the way to D and follow that back to B. So this is going to show us that there is a path between A and B, so we could actually return early out of our DFS here. But if you wanted to complete the full DFS cycle, you would backtrack from B, mark that as done since there's no other roads, backtrack back to A, and then you would visit the whole map.
Thanks, Vida. That was awesome. Okay, so as a conclusion, DFS and BFS are just traversal strategies. It's similar to how if you want to bake a cookie, you got to have the dough, you got to put it in the oven, and then like, boom, cookie, right? However, it's probably not the greatest cookie in the world. You might want to have to modify that recipe, right? You might want to add some toppings, use different milk. But at the end of the day, you have to have some dough. You got to put it in the oven. The same thing with DFS and BFS. They don't magically solve your problem. You will almost certainly have to modify them in some way to suit your specific problem. And just like Vida showed you earlier, sometimes they can both work, right? But a lot of the time, one is going to make more sense than the other.
Yeah, exactly.
Yep. Here we're going to have a comparison between BFS and DFS. They are actually really similar to each other. The biggest differences are in the data structures that are used to compare, that are used to work the two algorithms. So the BFS is going to use a queue, and DFS is going to use recursion, or if you want to do it iteratively, you're going to need a stack. They both have the same runtime because you have to visit every node, and you also have to visit each of the edges as well. So think of, you have to visit every single road in the fork and visit each fork at least or at most one time. And BFS is great if you're trying to find the shortest distance or just trying to find how many levels until something. Both work really well for printing out a path, but DFS can be more intuitive if a path is really what you're trying to achieve.
So we talked a lot about the different kind of questions that graphs can answer and the different approaches for traversing them. And we came up with this acronym that we hope is helpful for you to identify a graphing problem and to be able to look at an interview question and raise a little flag in your head to say, oh, this might be solvable through graphs. So the acronym starts with G, which stands for grids. These are questions that start with something like, you have a 2D array of blank, or a game is played on a grid. These are usually a key identifier that you can solve this question using a graphing algorithm. Another key identifier is relationships. So that can be between two people, two words, points on a geographical map. These are usually going to start raising some questions of, I see relationships between two nodes. This is already sounding like a graph with two nodes and edges in between them. Another identifier is what we're calling actions, or this or that. So that means that at every step of your solution, you basically have a choice to make of what action you take. An example of this is if at every step that you make during your solution, you can either go up, down, left, or right. So at every step, I have a choice, this or that. That's usually going to be a graphing algorithm. Another key indicator is paths. So finding if a path exists, you can listen for keywords like nearest point, shortest distance, furthest distance. These are usually related to graphing algorithms as well. And the last one that we have for you is hierarchies. So this is generally representative of a one-way relationship. So think manager to employees. And these are actually mostly related to trees. Trees are a type of graph and they can be solved using graphing algorithms. We will not be covering trees specifically in this video, but there is a separate video in the series that you can go check out that will go into trees in more depth. So now that we've identified the graphing problem, what do we do? First, we're going to visualize an example. So we like to construct a simple, verifiable example, something we can draw out, a version of the graph that we can look at and kind of reason out the solution to check our programmed solution against. We're also going to use this to identify what relates the entities in this example. So if you're looking at a map, it might be streets between destinations. If you're looking at a social network, it might be friendships between people. So you want to identify what is that relationship between the nodes in your graph, and it can really help to draw it out. So we know that a lot of interviews are often online. Feel free to have pen and paper with you. Just make sure to share out loud with your interviewer what you're doing. Once you've kind of visualized an example, we want to start planning our approach. So usually graph questions have a start and an end point. They're not always immediately obvious from the way the question is phrased, so it can help to define those. Then it can help to kind of talk out your approach and how you're going to make your way through the graph. Are you going to use DFS or BFS? And remember, these are just traversal strategies, so you'll have to make some adjustments to each approach. So this is where you kind of start thinking about, What do I need to add on? And how do I modify these traversals to fit my question?
All right. That was exciting. Now we get to like the really cool part. We get to go through some examples and really, really talk about things that Vito just outlined. Cool. Let's start with the first one, course schedule. So this should hit right home for the folks watching this. Let's say that you are given a total number of courses you have to take, a list of prerequisites pairs, and your goal is to find an ordering of classes that you should take to finish all the classes and graduate, right? So classes are labeled from 0 to n-1. Some classes have prerequisites, right? And the prerequisites are given to you as a pair. So the pair 0, 1 indicates that 1 is a prerequisite of 0. Note that there could be multiple orders here, right? You can take math and English or English and math, right? That particular order doesn't matter. So we just want to find some ordering such that we can take all the courses. All right, let's go ahead and dive into an example. But before we do that, there's a couple of things to highlight in this question. So there are a couple of things that stick out, right? Find an ordering. So already I'm thinking like, okay, like some kind of traversal, right? And some classes have prerequisites. Okay, that's like a relationship kind of thing. So the problem itself is giving me hints about how different things are related in the problem. But let's put this in our back pocket for a second. Let's look at a very specific example and see if we can dig anything else up out of here. So in this example, we have 4 courses to take, right? So 0, 1, 2, and 3. And here are the prerequisites. So 0 is a prerequisite for 1 and 2, and 1 is a prerequisite for 3, and 2 is a prerequisite for, or 2 is a prerequisite for 3. And here's just one output we can get from here. So we can take the courses 0, 2, 1, or 3. But we could have also done 0, 1, 2, and 3. So like I said before, there are different orders that work. So let's explore more into this example and see what we can dig up. Okay. We know that given a course, it has prerequisites, right? So we can't just like take a course. We also know that there's this idea of if I'm going to take a course, its prerequisites have to be satisfied. So that seems pretty intuitive. Okay, putting all that together, I know what classes I need to take. I know what each class's prerequisites are. I can now create a graph that represents this relationship. So we can have this directed graph right here. For any course, say course 3, for example, the edges indicate the prerequisites for that course, right? So course 3 is going to have 2 edges coming out of it to course 1 and 2, but 1 and 2 are just going to have 1 edge pointing to 0. So now let's analyze this graph. Now we have this structure here. What can we do with it? Okay, let's just start playing around with it, right? Let's just pick a course, right? We're just trying to test stuff and see what happens. So let's start at course 1. Doesn't matter. Well, we can't take course 1 because 0 is a prerequisite. Okay, so let's just follow the graph, right? Like intuitively, if you're a student, you would just go take that prerequisite, right? So let's go to 0 and take 0. Okay, we'll take course 0. We come back to 1. We take 1, but then there's no edge leading. There are no other edges leading outside of 1. So we're done. So the order is 0, 1. That seems kind of wrong. Okay, let's do another thing, right? Let's pick another. Let's start from somewhere else. Let's start from course 3. Okay, course 3 has 2 prerequisites, 1 and 2. So this is kind of like English and math, right? Like, does it matter which one you take? No. So let's just pick one, right? Let's pick one and see what happens. Let's say we pick 2. Okay, so we go to 2. We also can't take 2. All right, so let's just naively just keep going, right? Can't take 2. Let's take its prerequisites, go to 0. Okay, so we take 0. We come back, we take 2. We come back, we take 3. But can we take 3? We can't take 3 because we haven't taken 1 yet. Okay, so we now have to go to 1. Can we take 1? We can take 1 because we took course 0 when we tried to take course 2. Okay, so things are kind of lining up. So we backtrack to 3 and we can finally take 3. Okay, let's see if we can put it all together. Things have become a little bit more clear here. It seems like we can start at any course. If that course has prerequisites, we just need to try to take one of them, right? Then when we get to that course, if it has prerequisites. We take one of those prerequisites, and we only take a course when we actually backtrack, right? If after backtracking we haven't taken all the courses, we can just pick another starting point, right? Okay, let's see how this all kind of like comes together. There is a problem though. Suppose 0 had a prerequisite of 3. Okay, let's just try it out, right? Let's start at 0. Okay, we try to take course 0. We can't, so we go to course 3. We can't take course 3 because we have to take 1 or 2 first. Okay, let's pick 2. So we go to 2. We can't take course 2, but then we go back to 0. This hold up, right? Nothing. This doesn't feel right, right? This is a cycle. Okay, so it seems like if we detect a cycle, no order will allow us to take any of the courses. So this is a really important distinction. Okay, now we have all the details on the table. Let's see where we can take this. All right, DFS or BFS? Well, we can pick any course we want to attempt to take. But if we can't take it, then we just pick one of its neighbors, right? We can do this, we can do that, right? So we can pick one path or another path in the fork, right? So this kind of fits our analogy of fork and road, this or that really, really nicely. So DFS is actually a natural fit for this. The only modification we have to make is that we have to do extra work when we're backtracking, right? So when we come out of a fork in the road, we have to make sure we take that course, right? And you also notice that we're asking a lot about what are the courses, who are your prerequisites. So we'll almost certainly need an adjacency list here to make this more efficient. All right, let's put it all together. Let's create our algorithm, right? Okay, we need our adjacency list. Let's create that. We're going to use a map that maps from integer to set of integers. Remember, the integers represents the courses. We also need to track 3 things, right? We need to track the output, of course. We have to track courses that we've taken in general. And we also have to track courses that we've seen while we were trying to take a particular course, okay? So given those 3 things, we can then perform DFS. For each course, if we've taken the course, skip it, we're done, right? If we haven't taken the course, we just perform DFS on that particular course, right? If a cycle is detected, we're done. We don't need to go any further. However, if we haven't detected a cycle, when we backtrack on our way out of the DFS, we have to make sure that we take the course, and then we have to clear our scene structure so that we can prepare for the next DFS run. At the end of the day, we return the output. Okay, here's the code, right? Here's the code. Okay, so the first line, not ignoring the function header, the first line, this is where we construct the adjacency list. Okay, then the next 3 lines there are going to be setting up our taken, seen, and output structures like we talked about. The main code is really in that for loop, right? We're going to arbitrarily start from course 0 because as we said before, it doesn't matter where we start, right? So start at course 0. If we've taken it, keep going. We don't care. Then we're going to perform DFS on that course. If we detected a cycle, we're also done, right? Return an empty array. If we haven't detected a cycle, great, right? We come out of the DFS, we reset our scene, prepare for the next run. The DFS here is actually going to be quite vanilla. So this should really look quite similar to a lot of the other DFS codes, different examples that you've seen. So the only major difference is we need to worry about cycles, right? So conceptually, we know we're at a cycle if we haven't taken a course, but we've seen it before, right? So that means we detected a cycle. So if that condition is true, we return true immediately. If we've taken a course, then we don't need to be here, right? Go back, right? Like backtrack. But if none of those things are, none of those conditions are met, we then go ahead and say we've seen the course, but we haven't taken it yet, right? Before we take the course, we have to make sure we perform DFS on each one of its children, right? So this is I can take one or two. I'm going to take one and take it all the way to 0, right, before coming back. And then once we're done looking at all the neighbors, we then take the course and then add it to the output. Cool. And so here are the helper functions that we used. So we have here the get prerequisite map. So all this does is it just runs through the prerequisites that we were given. And for each one, we're going to take the first item, that'll be the key to our map. And then the second item would be part of the set that we append to that key. And then secondary, we have these two int arrays. So we are using Java here, which is a little bit interesting language. So we've been working with lists, but the output needs to be in terms of an array. So we just use this code where we create an array of the size of the list and go ahead and insert the elements in the order of the list.
Awesome. Thanks, Chuck. So actually, Chuck and I both took this question separately without talking to each other. And when we ended up coming together, we realized that we had pretty different approaches that both solved the question. So we wanted to walk you through another way that you could potentially solve this. So when I started looking at this question, similarly to Chuck, I kind of started with like a storytelling approach of how would I do this in real life if I'm looking at a course catalog. So for me, my first thought was to take the classes that don't have any prerequisites. I know I can take those immediately, get those out of the way. Now that I've taken those, new classes have essentially opened up, right? Like they have no more prerequisites because I already took it. So now I'm going to take these new classes and I'm just going to repeat that until I take all the classes that I need. So let's visualize this. I want to point out here that my graph, while it looks the same as Chuck's, my arrows are actually pointing in the opposite direction. This is because I use arrows to represent the courses that satisfy another one. So 0 in this example is a prerequisite for 1 and 2, and taking 0 will open up 1 and 2. So let's get started. I'm going to first take the classes that don't have any prerequisites, so that would be 0. Now that I've taken 0, I kind of remove it from my mental map, my mental visual, and I can see that 1 and 2 have now opened up. I've done all the prerequisites I need for them, so I can take 1 and 2. Once I take those, I do the same thing, and I can see that now 3 is opened up. So that's going to be kind of my visual order of just before even trying to map this to an algorithm, this is how I would approach the question. And just looking at this example, I noticed that I'm kind of going down by levels. I started at the top level, took 0, then I got to kind of this middle level where it didn't matter if I took 1 or 2, and then I got to the last one. So this immediately is making me think this looks a little bit like BFS. But I know that we're going to need to adapt it. So kind of talking through what I visualized and putting it into a little bit more of a concrete example, I need to take one level of courses at a time, and the order within a level doesn't matter. Then I need to keep track of what courses unblock each other. I can only take a course if it has no prerequisites left. And I want to start with the classes that already have no prerequisites. Immediately, this is making me think, keeping track of what courses unblock each other, just like Chuck said, that's making me realize that I'm going to need an adjacency list here. When I say that I can only take a course if it has no prerequisites left, I'm also noticing that's not going to be regular BFS. Usually I can go to the next level no matter what, but here I'm going to need to make some adjustments. So let me walk through another really quick example to really show you the difference of this modification. So let's say that I have a classes taken list and I have a queue list. And I've updated my example a little bit to be more uneven, to kind of give me more of an edge case to make sure that I'm running through the sample code in a way that I can verify visually. So I'm going to start with the classes that have no prereqs. I'm going to start with 0 and 2. The order here doesn't matter. And I'm going to put them on my queue. Let's start by taking class 0. And I'm actually then going to take all of its neighbors. So I'm going to look for 1, and I'm going to add that to my queue. Now I'm going to pop my queue. I'm going to try to take class 2. It has no prereqs, so I'm good to go. And then I'm going to add all of 2's neighbors, or I'm going to try to. So this is where I start asking, can I add class 3 yet? I actually can't. In a normal BFS, I would, but here I still have to take 1. So this is where my modification for BFS is going to be coming in. I'm not going to add class 3 yet. I'm actually going to go back to my queue and I'm going to take class 1. Now that that's taken, I'm going to check all of 1's neighbors. That's going to give me 3. And this time I can add it to the queue because it no longer has any prerequisites left. I'm going to take class 3, and that's kind of how I go through my courses. Awesome. So let's start putting that into code. So first, let's create a map that maps a course to the list of courses that it unblocks when you complete it. So this code is pretty straightforward. I'm looping through my input. First, I'm going to create this empty class to unblocked map, and then I'm going to actually populate it. While I'm here, I noticed that I'm also looping through all the courses, so I might as well do it at the same time. I'm going to look for cycles here. So if I find a class that unblocks a class that says that it's supposed to be blocked by this one, I'm noticing a circle here. That's going to tell me that I can't actually take all the courses that I need, and this is an edge case that I know that I need to handle. Awesome. Another helper function, pretty similar, but this one is going to map a course to the number of prerequisites required to take before I can actually take it. So in my previous example, 3 had 2 prerequisites. Again, pretty straightforward. Now let's get to the actual BFS here. Now that I've created both of these maps, I'm going to create that queue, the same one that I was talking about in my walkthrough. I'm going to find and populate my queue with the classes that have no prerequisites. So that's going to be my starting point. While there's still stuff on my queue, I'm going to pop off the head, add it to my list of taken classes, find all of its neighbors, but I'm going to only add its neighbor to my queue if that neighbor has no more prerequisites left. So while I'm here, I'm also updating and decreasing the number of prerequisites of my neighbor. Now that I took my own class, I know my neighbors have 1 less prereq left. If they have none left, I know I can take them now. But if they have more, I'm kind of just ignoring them from now. I'm not even adding them to my queue. There's some cleanup code of just making sure, similar to what Chuck said, returning an array in the format that is expected and handling some edge cases, making sure that the number of classes that I did actually end up taking are the same as the number of classes that I'm expected to take. And you can check out the full code in the attached information.
Cool. Thanks. It was actually pretty exciting to see how different Vita's solution was. I was fully convinced there was only one way to do it. Obviously, I was wrong. Okay, so the next exciting question here is word ladder. This one is actually a really, really cool one. So you are given 2 words, begin word and end word, and a dictionary word list, okay? And you want to return the number of words in the shortest transformation sequence from begin word to end word, okay? Like, that's a mouthful. Okay, a transformation is a transformation counts if the next word differs by 1 letter, right? So each word in the transformation is going to differ by 1 letter from the word before it. And the last thing here is that begin word may not be in the word list. Fine. Okay, let's highlight a few things like we did with the last problem. I see shortest transformation sequence. Immediately, I'm thinking like, all right, this is probably like a BFS problem, right? But, let's not jump to any conclusions yet, right? We also see each transformation must differ by 1 letter. Again, like, I'm thinking relationships here. How are words related? This is kind of painting a picture of what we could construct as a graph. All right, let's go through an example. Start word is hit, end word is cog. Okay, so here's our word list. And you can test this for yourself, but the shortest transformation sequence would be from hit to hot to dot to dog to cog. So number of 5 words. There are actually other 5-word sequences you could have picked. This is not the only one out there, but this example is going to also show us that we don't really care about the words themselves, but we'll get to that. We'll get to that. All right, let's go through the relationships. Pretend you're in Vegas, right? You're in Vegas, and like you're at the slot machine, right? Okay. The word that's currently on the slot machine is your start word, right? That's hit. Okay. What if you just started at the first position and just changed one letter, right? So if we change the H to IIT is not in the word list, right? So we'll call this a candidate, right? Every new word we create, we'll call this a candidate. It's not in the word list, but it's also not end word. So not what we want, right? So let's just change the letter again. So we change I to J. Okay. Also not in word list, also not the word. However, we'll just keep going, right? So we'll run through the entire alphabet, right? In that first position. And if none of those candidate words are end word or are in the word list, we just say, we try with that first position and we check the second position. Second position, same idea, right? We're gonna start from I, then we're gonna run through the entire alphabet. J doesn't work, nope. K doesn't work, nope. Okay, we'll run through the entire alphabet. If none of those work, then we go to the third position. And we'll do the exact same thing again, run through the entire alphabet. Okay, so then it begs the question, who are the neighbors, right? Like, what are we doing here? Okay, so given the word that we're processing, right? The word that was first on that slot machine when you showed up, every new word you create by changing a letter, we're gonna call that a candidate. Every candidate that's actually in our word list, we'll call that a word that's viable. The viable words, those are our neighbors. So given the word, its neighbors are all the words created from running the slot machine that are actually in the word list. So now we can actually go ahead and create our graph. Okay, here's a graph for the hit example, right? So for any word, as I said before, its neighbors are the words that differ by one letter in any position, right? And you can see here that if we start with hit, then our options are a lot more clear, right? From hit, we can get to hot. From hot, we can check lot and dot, and so on and so forth. So we have this idea of like choices we can make because our goal, remember, is to find cog in the shortest distance. All right, so how do we do this? All right, there are two ways that are like immediately kind of like come to mind, right? We can start with hit and just literally try every path until we get to cog, right? Or remember what I said earlier, we don't actually care about the words in between. We just care about getting to cog, right? We care about how many steps, how many distances it takes to get there. Does that sound familiar? Hopefully it does. So DFS or BFS, I think BFS here is the one that is the most natural, right? We really only care about the distance from start word to end word, right? So we run a BFS on this problem and we just track the total distance. That distance as at the end is the shortest transformation sequence. All right. Okay, so now some modifications we have to make. The BFS strategy as a vanilla strategy is going to work really well for us. We just have to make sure we track the distances, right? We also don't need an adjacency list. Remember, think about how many different words we have to actually check given a main word. We only have to check 26 letters in the first position, 26 in the second position, 26 in the third position. This is a constant number, right? In the English alphabet, there are only 26 letters. So actually, this is a constant time operation. So we don't necessarily have to create an adjacency list if we don't want to. Okay, so let's see how this works out. So the algorithm starts off as regular BFS. So we add start word to the queue. Our total distance is going to start from 1 this time, right? The first word is going to count as the first transformation, right? So while the queue is not empty, we're going to go ahead and store the current size of the queue at that time. That tells us how many words are in that current distance, right? So while there are still words in that current distance, we're going to dequeue the word. That word that we dequeue is our main word, the word that's on the slot machine, right? If it's end word, we're done. Okay, if it's not end word, we're going to run the slot machine. And for each new viable word, we're going to add that to the queue. Then we're going to subtract how many things are in that distance every time like we encounter them. Then at the very end of that, we're going to increment our total distance by 1 because we just processed the words that are at the current distance. Then at the very, very end, we return total distance. Okay, here's the top level code, right? Okay, so if the end word is not in the word list, we can immediately just say it's not possible, right? Because you got to be in the word list. Okay, ignoring that, okay, we're going to first create a set out of our word list. That'll help us with very quick lookups. And then we're going to bootstrap start word onto the queue, right? So this is just sort of regular BFS here. And then the setup looks a little bit different, but it's mostly still looking like BFS, right? So we have distance set to 1 initially. While the queue is not empty, we're going to capture the current size of the queue. Then we're going to do our current distance logic, which I'll get to next. All right, here's like the core logic of this whole thing, right? So the first line there is we're going to grab the first item off the queue, right? This is our word. If it's the word we're looking for, we're done, return distance. If it's not the word, first things first, we're going to take that word and convert it into a character array. This is going to give us the least amount of string operations, right? Array operations are going to be less expensive than string operations. And it represents our slot machine a lot better, right? So we're going to go ahead and run through our slot machine. Okay, so for every candidate word, we're going to do two things. Are you in the word list? And have I not seen you before? Okay, if that's true, then we're gonna go ahead and add you as a viable word to our queue. All the while keeping track that we make sure we don't revisit you later on. Then we reset the character, right? And then prepare for the next slot machine run. At the very end, we subtract the distance size minus every time we process a node at the current distance.
Thanks, Chuck. What a fun example. We hope that these examples have helped you gain a little bit of insight into how to recognize graph questions, how to solve them, the different approaches that you can take, and hopefully you're able to use this in an upcoming interview. We highly recommend checking out the other videos in the series as well to learn more about other interview gotchas and questions. Don't forget to visit google.com/students to explore open jobs and apply to join us. And we hope to see your application soon. Thanks everyone for tuning in today, and thank you, Chuck.
Thanks, Vita.